Hello, Accelerated Chemistry students. This is Ms. Crystal Foley, and this is your Chapter 25, Section 3, notes all over fission and fusion. So let's start talking about nuclear fission. So when the nuclei of certain isotopes are bombarded with neutrons, the nuclei is going to split into smaller fragments. This process is called fission. So nuclear fission, the splitting is the splitting of nucleus into smaller fragments, releases large amounts of energy, and is used to generate power in nuclear power plants. So it's often initiated with a neutron bombardment. So let's look at this picture. We have uranium-235 on the left. We're going to hit it with a neutron, and what it's going to do, it's going to release lots of energy, and then it's going to split into smaller isotopes. So strontium-90 and xenon-143. And then it's also going to release neutrons in the process. So in a chain reaction, some of the emitted neutrons react with other fissionable atoms, which will emit neutrons that react with still more fissionable atoms. So if we look at this, you're going to have not one atom in a container when we do this. You're going to have multiple. So you're going to hit one of the atoms with a neutron. That's going to split and release neutrons. Those neutrons are going to hit other uranium atoms, which are going to split. And those uranium atoms are going to release neutrons. And it's going to keep going and going and going. So the number of fission and energy released can rapidly increase. So the atomic bomb explosion is an example of an uncontrolled fission reaction. So let's watch this video.
Fission occurs when a neutron is absorbed by the nucleus of a uranium-235 atom. The extra neutron causes the atom to become unstable and divide into two or more smaller units called fission products. This process generates heat and more neutrons. Uranium atoms nearby then absorb the extra neutrons and undergo fission, which sustains the reaction.
So that's how fission works. Pretty quick and easy, straight to the point. So let's talk about nuclear reactors. So nuclear reactors use controlled fission to produce useful energy. The reaction takes place within uranium-235 or plutonium-239 fuel rocks. So there is a coolant that's going to absorb the heat produced by the controlled fission reaction, and it's going to transfer the heat to water, which will change into steam because the water is going to get heated up and it's going to go from a liquid to a gas phase. So then the steam is going to drive the turbine, which will drive a generator, which will produce our energy. So if we were to look at a nuclear power plant, these are all the guts and pieces of the nuclear power plant. So the neutron moderation is a process that slows down neutrons so that the reactor fuel can capture them to continue the chain reaction. So moderation is necessary because most of the neutrons produced move so fast that they will pass right through a nucleus without being captured. So water and carbon in the form of graphite are good moderators. So to prevent the chain reaction from going too fast, some of the slowed neutrons must be trapped before they hit the fissionable atom. So neutron absorption is the process that decreases the number of slow-moving neutrons. So control rods are made of materials such as cadmium, which are used to absorb these neutrons. So when control rods extend almost all the way in the nuclear reactor core, they absorb many neutrons and the fission occurs slowly. As the control rods are pulled out, they absorb fewer neutrons and the fission process speeds up. We're going to see this when we do a FET simulation in class tomorrow. If a chain reaction were to go too fast, heat might be produced faster than the coolant could remove it. So this is when a meltdown or a nuclear reactor core could break and not work sufficiently. So let's look at this picture. So in this picture, we have behind the control rods and the fuel rods is circulating cooling fluid. So the fuel rods contain the fissionable radioactive source. The control rods can be pushed down further into the fuel rods or pulled up. And they're going to regulate the amount of neutrons that are absorbed. And the cooling fluid is going to act like the moderator, which is going to slow down those neutrons so they're not moving so fast with so much energy. So obviously nuclear reactors are going to produce waste. So the nuclear waste is going to come from the fuel rods. The fuel rods are made of fissionable isotopes, either uranium or plutonium. And during fission, the amount of fissionable isotope in each rod is going to decrease. So eventually the rods will no longer have fuel to ensure that the output of the power station remains constant. So the spent fuel rods are going to be classified as high-level nuclear waste. So all nuclear power plants have holding tanks or swimming pools to put the fuel rods in. Water cools the spent rods and also acts as a radiation shield to reduce the radiation levels. So at some nuclear plants, the storage pool has no space left. So finding appropriate storage sites is difficult because the high-level waste may need to be stored for a long time. So now let's flip gears. We've talked about fission. Now let's talk about fusion. So the energy emitted by the sun results from nuclear fusion. So fusion occurs when nuclei combine to produce nuclei of greater mass. So think fuse. We're fusing atoms together. So in solar fusion, hydrogen nuclei, or remember, we are also going to call those protons, fuse to make a helium nucleus. So this reaction is going to also produce 2 positrons and lots of energy. So fusion reactions in which small nuclei combined release much more energy than fission reactions, in which remember, fission reactions have large nuclei splitting into smaller ones. So fusion reactions occur at very high temperatures, in excess of 40 million degrees Celsius. So what does that mean? That means that it's very hard for us to trap that energy. And so the potentials for fuels are inexpensive and readily available. But fusion happens at that high temperature. So there's no material that we have made so far that will be able to contain that reaction once it's started. So the high temperatures required to start fusion reactions have been achieved using fission bombs. So such a bomb has a triggering device used for setting off a hydrogen bomb, which is an uncontrolled fusion device. And this process is of no use, however, as a controlled generator of power. And that is the end of your Chapter 25, Section 3 notes all over nuclear fission and fusion. And remember, all the information on these Google slides has been acquired and adapted from Pearson's Chem's 2012 edition of the textbooks, Resources CD, and PearsonChem.com. Thank you.